I'm Antonio Sala, and in this video we are going to discuss the heuristic, trial and error, intuitive, let's say, tuning of a PID controller for a double integrator process, which is, let's say, position control of a mechanical system in which my force is the manipulated input. For brevity, in this video we will consider only the proportional and derivative controller tuning and some derivative action options and tweaks. The full PID, adding integral action for better disturbance rejection performance, will be discussed in a sequel video. So, if we think on the problem we are going to discuss, we will have an object with, say, 0.5 kilogram mass, and I will be able to apply a force to it. We are making abstraction of the technology. We don't know if that force is, from compressed air and some pressure regulators, from some electromagnetic actuator, or if it's, a drone with propellers. Just we make the abstraction that we can exert a desired force in a reasonable fast way with some technology. So this is my system, and then I wish for this system to move, let's say, 1 meter to the right. So this will be the set point we will simulate, and my saturation limit of my force will be 1 Newton. So that will mean that we will not be able to move 1 meter in, let's say, 1 microsecond. How fast can we move that? Well, my maximum acceleration will be force divided by mass. So 1 over 0.5 will give me 2 meters second squared maximum acceleration. So for a uniformly accelerated motion with 2 meters second acceleration, this is the formula for the position. It gives exactly t squared. So if I solve for the time it takes to reach 1 meter, well, it's prepared. So it takes 1 second. So in maximum acceleration, it will take 1 second to move from 0 to 1. So if the task my controller must fulfill is that one, I will not be able to achieve settling times faster than 1 second in order to, to suitably dimension which kind of performance we wish to extract from my plant. So good. Then, which is the transfer function of this double integrator? Well, as mass times acceleration is force in Laplace domain, zero initial conditions, acceleration is the second derivative of the position p of s. So second derivative is multiplying by s squared. So we have this equation in Laplace domain that, of course, in transfer function form, solving for the position is 1 over ms squared transfer function times f of s. So well, with my particular mass of 0.5, this will end up being 2 over s squared as transfer function we are going to simulate. And indeed, if we type that transfer function into MATLAB and we execute my PID control simulation application that I used in other previous videos, the window opens. So we load my system from the workspace, and then we can switch on the most basic control action, which is the proportional control, and let's see what happens. And we'll start by removing saturation to see what linear theory predicts, and we'll delve with saturation and other tweaks later on. So if we increase proportional gain, well, seems unstable or something like that. Well, this doesn't look good. Well, strange things happen. Let us zoom out to see what's happening. Well, we see sort of oscillating behavior, and it seems that the oscillation amplitude does not decay to 0, but does not increase to infinity. And indeed, we can prove in theory that we would predict a marginally stable behavior, so sustained oscillations. And in fact, the oscillation frequency in here, for instance, I have like 2 periods in 6 seconds with 2.2 gain, and if I multiply the gain by 4 to 8.8, then frequency multiplies by 2. I have 4 periods. Of course, this can be predicted in theory, but intuition can also help us in thinking on this behavior because, well, what the hell is proportional control? Is something which exerts a force proportional to the error. So we can imagine having a virtual spring connected to the center of my mass I wish to position and to the set point. So if I exert a force proportional to the error, it will be equivalent to placing this mechanical spring. And in fact, a proportional derivative control can be sometimes achieved with mechanical adjustments in suspensions, let's say. But okay, if I do it in software, I can change the gains in a second just by typing the new gain in the keyboard. And if I do with mechanical components, I would need to change the spring. So that's why modern control systems use software components, but car suspensions and mechanisms devised one century ago might use some mechanical control elements and levers and screws, springs and whatever. So our proportional control is just a software-based spring, and then if we imagine the behavior of this system with no friction, this system would oscillate forever, left and right, and that's what we see here with this software spring. Of course, we can do equations, but if you recall what a mass spring system is, then you perfectly understand what's happening. So the idea is that we do need damping. Damping will be called derivative action if we do it in software. If we do it in mechanical hardware, it would be, let's say, adding a damper somewhere in my mechanism. But again, software-based damping is much more flexible because I can change the damping constant with my keyboard. Then, for instance, if I add this damping, then the force of the damper will be a constant that in control jargon is called T sub D times the relative speed between the two ends of the damper, which is the derivative of the error, the difference between set point and actual position. So this is the first option of inserting damping by my software. Second option would be inserting rolling damping. That's another way to absorb energy so that my spring-induced oscillations end up stopping. And well, in that case, the damping force will be the constant times the derivative of the position, not of the error. Well, the thing is that software-based damping, derivative action, can easily program the first option, the second option, or even intermediate ones. This is the C coefficient here, in which C is what multiplies the set point derivative. So if it is 0, we are damping with a rolling damping, let's say. And if it is 1, we are fully damping the error. And if it is 0.5, then we are splitting the damping between, 50% of the damping to this ping damper and another 50% of the damping to the rolling friction. So, well, in software it's as easy as adjusting a slider, and we'll do that later on. But we'll start with this just rolling friction and we'll see what happens. Then, in this case, if I increase my rolling friction, then oscillations quickly dampen more and more. And well, for instance, like here, we have a very nice damping, but okay, look, we are achieving a settling time of half a second, and that is too fast according to my saturation limits. I just asserted previously that faster than 1 second was not possible, and indeed if I turn saturation on, things take 1 second, so I will reduce the proportional gain until my rise time is roughly a second. This 2.5, let's say, proportional gain, And then I will tweak the damping so that now I have a very nice set point response, no overshoot, taking 1 point something seconds. And indeed, if I activate saturation, there is no big difference between saturated and non-saturated behavior because my required settling time is slow enough. So with this tuning, somehow I would be happy with my rolling friction equivalent damping. Then, well, okay, this is nice set point tracking response. But I have several problems. One, ramps are not followed too well. In here I have a force disturbance and I have position error. We'll discuss that in 5 minutes. And we also have high frequency noise amplification. So let's start with that noise amplification. Proportional control amplifies noise by the proportional gain, but derivative control exacerbates that effect because, well, if we zoom in, the signals with noise have fast changing slope, so the derivative is 200 minus 1000 or whatever. So the derivative in a frequency response interpretation, if sinus of some omega t is present in the signal, then the derivative will be omega sinus of omega t. So the high frequency amplification is exacerbated by derivative components. And indeed, this we see in the manipulated variable a lot of noise. Is this good or bad? Well, depends. If we are moving mechanical systems, this may be bad because, we may induce high frequency vibrations that excite some resonances that break some things with fatigue. And on the other hand, in some applications, it's good to overcome stiction because of Coulomb friction, let's say, because continuously bumping up, down, left, right, my thing I am trying to move will diminish the deleterious effect of Coulomb friction stiction. So, well, depends on your application. You may be happy with this or not. Then, if we wish to filter noise a little bit more, if I do not filter noise, this is a cutoff frequency of my noise filter. If I put 1000 radians, then it's pure noise. In theory, derivative action cannot be realized. It would have infinite high frequency noise amplification, but okay, if I filter 10 radians per second and it's not good enough, then I can go to, let's say, 4 radians per second, and the signal is much cleaner, but we start to see that damping is less effective and oscillations appear because the settling time of my filter, let's say, starts influencing the slow dynamics I wish to control. So maybe, depends on my signal to noise ratio of my practical sensors and the level of disruption to my dynamics. I need to decide on a compromise, let's say a trade-off. And well, for instance, in here I will decide 6 radians per second as my sensible option, a little less damping like here. So, well, this will be my choice. And then, saturation is still sensibly close to what I wish. Then, well, this would be my perfect, let's say, PD tuning for set point tracking. What happens with ramp tracking and disturbance rejection? Well, ramp tracking is somehow bad, but it could be better if I used this first option for damping, because then if reference moves with a certain speed, I will have a force proportional to that speed of motion of my reference, and then reference tracking would be better. And in fact, we'll discuss when we deal with the theory that we could track references with 0 error with this option for the damping, which will be C equal 1 in my simulation here. And in it you see that the reference is going to be tracked in a much better way when the ramp shape starts. But well, if I disconnect saturation, This much better ramp tracking involves a much higher overshoot when having step setpoint changes, because, well, there is one strange effect in the sense that step setpoint change means an infinite speed change in just an infinitesimal time. So this mass would in theory receive an impulsional infinite force when I have a step setpoint change. That is called, let's say, derivative kick. Indeed, if we see the amplitude of the input signal, as I am filtering the derivative action, this initial peak does not grow to infinity, but it grows to 11. And on the other hand, if I use my rolling friction option, instead of 11, it's just 2.5, which is the proportional gain. So this effect is the so-called derivative kick, an abrupt, extremely high force command for step setpoint changes, and, well, depending on your application, you will be happy with it if steps do not occur but ramps do occur, because then you will have a better ramp tracking. But if you are not happy with it, then okay, you can play with this slider and adjust it to your choice. And then, well, in this case I will stick with rolling friction because, well, I am interested in a beautiful step response. So this is the step versus ramp discussion with this kind of two options of damping. And as I said, you can settle for something in the middle if you have a mixture of steps and ramps. And the amplitude of that derivative kick also depends on the cutoff frequency of your noise filter. So, you need to tweak everything in order to fit your requirements. So, well, the issue is that after some tweaking, we may consider that we are satisfied with this setpoint tracking response and ramp tracking response. And, well, there is some disturbance rejection steady state offset in the final part of the simulation that will need to be corrected with integral action. But for brevity, we will leave that for a second video jointly with further comments and discussion. So for the moment being, we will stop here. And if we recall with what we have discussed in this video, we discussed control of a half a kilogram mass with force being manipulated variable. We discussed how proportional control did not work. It was not exponentially stable. We added some damping, and we discussed two options for damping: error damping, derivative of the error, or rolling damping, derivative of just the output signal, and that had different behavior in ramp tracking and step overshoot. And we also discussed the derivative action filtering in order to handle somehow the high frequency noise amplification. So if you are in your first control course, maybe you are not interested in the disturbance rejection task, and then with this setpoint tracking performance, maybe you are happy. So we'll end the video here. Thanks for watching.